realm of superficiality and take the big picture in. Let's just launch this discussion with what happened last summer. And we may have talked about this, but I think it was such an important wake-up call that it's perfectly valuable to revisit it. Mm-hmm. And this was June 29th, which is basically one day away from Asteroid Day, right? Asteroid Day, remember, the Tunguska event of 1908, June 30th, right? This is the peak of the Taurid meteor shower. And we now designate, so the Taurid meteor shower lasts roughly from a week before that to a week after that. It's an older meteor stream, more diffuse, because the older a meteor stream is, the more diffuse it'll become. Some of the younger meteor streams, the Earth will pass through the stream in a day or two. It takes Earth literally 2 to 3 weeks to pass through the entirety of the Taurid stream. It's more diffuse. That diffusing, the degree of diffusion is going to be a yardstick in a sense to let us know that stream is probably old. My guess is that the stream, from what I've seen, that it's probably between 25 and 30,000 years old. That it resulted from the fragmentation of a very, very large comet between 25 and 30,000 years ago. And most of it is cleared out by now, but this item, this asteroid could have been part of that stream, see, because it's June 29th. That's the peak. The peak is 29, 30, 31, right in there. Remember Tunguska, June 30th, see. So the timing is suspicious to me of this, but it's 2024 MK was the name of the asteroid. It flew past the Earth well within the lunar orbit. It was only discovered on June 16th, right? So it passed the Earth on June 29th, so the 16th, so what are we looking at? Less than 2 weeks between the time it was discovered and the time it just whisked by the Earth. A cosmic whisker missed the Earth, right? The asteroid was estimated to be between 5 and 800 feet in diameter. Now, Tunguska was about 150 feet in diameter, but remember, if we're thinking just for ballparking, the volume of a sphere, right? So the volume of a sphere, it scales by 4/3 pi radius cubed. In other words, take the radius, cube it, multiply that by 4/3 pi, and you get the volume of the sphere. Well, we could do the calculation quick here. I may have done it already here. I think I already did it. If you're going to do it, that's awesome. 4/3, is 1.33. Mm-hmm. So put in 75 radius of Tunguska.
That's what it was. Okay.
Okay, and then go times. First, back up. You're going to put in 75, the number of feet. Raise it to the third power. If you've got an x to the something key.
Yeah.
Okay. Then raise it to the third power. Then multiply times pi.
Okay.
And then that times 1.33. And tell me what you get.
I get 1,762,728.
Okay, 728. Now, can you put that in your storage?
Mm-hmm.
Okay, put that in storage. And now go 400
okay,
to the third power.
Okay.
Times pi times 1.33. And whatever you get, divide that by what you just put in your storage. And that's how many times more massive MK4 was than Tunguska.
151 times.
That sounds about right. So think about that. Now, what was Tunguska? It was like a 15 megaton bomb.
Yeah.
Right? Could wipe out completely annihilate any urban area on Earth. Tunguska alone. Now we're looking at something that's 100, 150 times. And see, also, here's something else to be kept in mind. Tunguska was low density. It was like a snowball, right? This thing was a rock. So its density is way greater than Tunguska. What does that mean? Well, it means its potential energy is going to be that much greater as well, see? So saying it's 150 times more destructive is possibly also just conservative. So what would that do? Well, here's sort of a breakdown, okay? Here I got it right here. This asteroid was estimated to be up to 800 feet in diameter, making it roughly 150 times more massive than the Tunguska object. With only a slightly different trajectory, this object could have collided with the Earth, causing an explosion with the power of at least 5 to 600 1 megaton bombs. So that would be, that would be like almost a whole nuclear arsenal unleashed. This is more than the combined energy of all nuclear weapons presently in the world. It would have blasted a crater 2.5 miles wide and 1,500 feet deep. So imagine that you're a geologist, this event has happened, it's months later or whatever, and scientists are actually finally able to get to the impact site to study it. And you're going to come walking up and you're standing on the rim of a hole that's 1,500 feet deep and it's 2.5 miles to the other side. That's one big hell of a hole.
That's a huge hole.
The fireball generated by the impact would have been over 3 miles in diameter. In a densely populated area such as the east coast of the United States, more than 1 million people would be instantly vaporized in the fireball or killed from the blast. Another 200,000 people would die from the 240 decibel shock wave. In other words, you'd have 200,000 people dying because the sound of the explosion killed them. Right? About 500,000 people would receive third-degree burns, and another 2.5 million would suffer from second-degree burns. Within 9 to 13 miles of the blast center, survivors would experience severe lung damage and ruptured eardrums. Within 25 miles of the impact epicenter, trees would be knocked down and ignite into flame. All or most buildings would collapse up to 22 miles from the impact site, and houses within 30 miles would be destroyed. An earthquake of at least 6.3 on the Richter scale would kill thousands more people and be felt up to 40 miles away. In other words, 40 miles away from the impact, you would feel the ground shake, probably farther than that. Peak wind speeds emanating outward from the blast would reach nearly 8,000 miles per hour. Inside of 20 miles, it would feel just like being inside of an F5 tornado. Now, that's what just missed us on June 29th. See, people are just like, that's what we're trying to do, Becket. We're trying to get people to start paying attention to the big picture here, right? I think that's why we're doing this podcast together.
That's exactly why we're doing that.
And there are many components to this. Now, we can look at this and we can go, within the scale of cosmic events, that really isn't that major, right? That's not going to cause... Locally, yeah, it's going to wipe out everything, but it's not going to cause a global mass extinction.
Right.
Right? Yeah.
It's just going to cause a lot of damage to a city or a civilization. And even that, like what we were talking about last week, there's evidence of things that pale in comparison to that.
Mm-hmm. Yeah. So I went on and I this is what I wrote. This was written in September of last year. I wrote this in September. The natural calamities that could affect human civilization in profound ways are numerous. Yet the priorities of most of the political establishment entirely neglect these possibilities in favor of contrived scenarios built on cherry-picked science exploited to promote a preordained conclusion. that humankind is causing a climate crisis by the use of fossil fuels. But the irony of all this is that as we stand on the threshold of a new industrial civilization based upon plasma physics, if it is not suppressed, the whole question of fossil fuel use and CO2-induced climate change becomes irrelevant. The whole thing becomes irrelevant. So anyways, at some point we're going to talk about the 536 to 544 AD event that launched the Dark Ages, because that gives us another contrasting type of probably the combined effects of two impacts in a series of great volcanic eruptions that launched what we know as the Dark Ages, that pretty much was 3 centuries in extent, during which knowledge and learning was almost lost in large parts of the world. And there was a few places where it survived, like, for example, Irish monasteries. Whatever it was, there was a group of monks in Ireland that set about to preserve as much of the classical world learning as they could. So there's actually even a book written about how the Irish saved civilization. It's a very interesting approach, realizing that, yes, there have been these periodic dark ages that have engulfed the earth and have caused a major collapse or downfall of civilization, and creating a situation and environment in which the challenge just to survive becomes pretty much the overriding mandate of the times. Once that we get through that, then there's periods of revitalization, such as came during the High Middle Ages. When the Dark Ages came to an end between 900 AD and 1000 AD, and was replaced by the medieval warm period, the climatic optimum of the Middle Ages, we see society recovering within a century. And then within a century and a half of that recovery, the whole of European society have embarked upon this incredible, almost miraculous enterprise of building these great cathedrals. Only possible as long as the environment is conducive. And then when the environment shifted again at the first phase of the Little Ice Age in the late 1200s and early 1300s, that started. The first blows came like right around the turn of the 12 to the 12 to the hundreds to 1300s. By around 1340, after like 4 decades of really challenging climate and spasmodic cooling, you had a series of collapses that had caused famine, and then I think it was 1342 when the bubonic plague swept over Europe. The plague seized and exploited people's weakened immune systems that followed in the wake of malnutrition, which followed in the wake of a whole series of agricultural collapses, which followed in the wake of global cooling. What caused that global cooling? It would behoove us to know. Was it solar? Probably so. It's probably a huge component of it that was solar. Was there anything else? Probably. Probably volcanoes were involved, because when you have a solar minima corresponding in time with major volcanic activity, you've got a recipe for disaster right there. Now, what if you add into that a cycle of periodic impact events, or what I would call cosmic dusting events, which can happen and last for anywhere from a couple of years up to, say, a decade before the particulate matter in the atmosphere clears out, right? But during that time, you've got this shroud that's reflecting solar energy back off, and the climate cools. Now, if you have any one of those 3 things happening together, or even all 3 of them, well, now you've got a recipe for disaster, no doubt. And we see those kinds of events happening periodically. The Greek Dark Ages that was followed by the rise of classical Greece, and then there was the 8,400 year ago event that lasted 200 years, and it was like a 4-degree cooling of the northern hemisphere, and that would have been a major kick in the ass to, society civilization trying to recover from the aftermath of the Younger Dryas and that whole terminal Pleistocene Holocene transition that took place. during which most of these great mega floods occurred there in that period between roughly 15,000 years ago and 11,000 years ago. I mean, our planet that we inhabit underwent an extreme shaking up event, a whole series of convulsions that took roughly 3,000 years to play out. And by the time this whole series of chaotic environment finally settled down, half of the great megafaunal species of the planet were gone, completely wiped out, completely extinct. The Solutrean culture of Europe was gone. The Clovis culture of North America was gone. Probably other cultures that survived but underwent tremendous having forced reorganization, migration from places. It was major disruption of whatever humans were doing culturally and in terms of civilization. Now, the thing I thought we could talk about tonight, because you brought it up and I have it ready to go, is this one example of one of these great hydraulic or fluvial events that occurred that seemed to characterize this transition from glacial to interglacial age. And we still don't know, really. I mean, we speculate. I think I have some ideas on that. But, you know, the thing about a glacial age, when glacial age comes on, unless there's some external force to pull the plug on it, it should be self-perpetuating. Because, look, it's a matter of albedo. When you know this, when you have what you don't wear, if it's really hot out, you don't wear black clothes, do you? You don't wear a black shirt, you wear a white shirt. Why? Because white reflects the heat and black absorbs it. The darker it is, the more heat it's going to absorb. The lighter it is, the more it's going to reflect. So if you have the onset of an ice age, and I was just reading about just the Fennoscandian ice sheet the other day, it was 4 million square kilometers in extent. That means that 4 million square kilometers of Europe was covered under snow that then became glacial ice. So all of that is reflecting heat back into space. Let's see what we could convert 4 million to that's about 1 million square miles, I guess, roughly. And but in North America, we had 6 million square miles covered. So what is that doing? That completely changes the albedo balance of the northern hemisphere. Right? It's reflecting all of this heat back into space. So the more the glacier grows, the more heat it's reflecting. It seems like it should be a perpetual, mutually reinforcing feedback loop that's going on.
Right.
But something interrupts that.
Something has to disrupt it. Yeah.
Something has to disrupt it. Or you've heard of ice house Earth at the point, that time way in the distant past, long before humans, when it looked like the whole planet was engulfed in an ice age, right? So there seems to be the consequence of this runaway feedback of a self-perpetuating glacier age, right? But we've seen at least 4 or 5 glacier cycles come and go in the last, 500,000 years, and it hasn't done that. It hasn't caused a runaway ice house that's caused the whole Earth to become locked down in glaciers. What happened in the most recent one? Well, that's the question. What happened, say, between 11 and 14, 15,000 years ago that brought the great ice sheet to an end and caused this rapid melting away of the ice sheet? Now, one of the things, we know it's rapid because we can see rapid sea level rise. In fact, there are CREs, catastrophic rise events. There were probably 3 of them. In other words, think about a 420-foot lower sea level at 15,000 years ago and now current levels, right? So that rise was not a uniform phenomenon. It was pulsed 2, 3. And then at the end of that, it actually overshot modern levels by 6, 7, 8 feet. Like 4,000, 5,000 years ago, and then settled back down to the modern, and actually went a little lower, and then has come back up, and now it's 8 inches higher than it was at the end of the 1800s. But so you have these catastrophic rise events, and they then, if they're associated with melting away of the glaciers, that meltwater now is either flowing directly off the glaciers into the global oceans, like it did particularly like on the west coast of the mountains of British Columbia, right? Because you had during the height of the Ice Age, they were all completely covered in ice. You had ice literally calving into the Pacific Ocean, right? Go to the East Coast, same thing. You had icebergs calving into the North Atlantic, So basically, if the ice is rapidly melting, that water is pouring directly into the ocean basins. Mm-hmm. However, what did you have, like 6,000 or 7,000 miles? Maybe, no, 3,000 or 4,000 miles. Of course, if you follow the irregularities of it, you had a glacier that reached from Washington State to New England that all headed onto land. So that melting has to traverse the land before on its way back to the ocean. And that's where it leaves these extraordinary calling cards in the wake of its passage. So the Bonneville flood was one of those events. But what's unique about the Bonneville flood, unlike when we look at the flooding earlier, you and we were talking, I told you about the discharge that created the Missouri River Valley, right? Well, we can look at the Columbia River, the Missouri River, the Mississippi River, the Hudson River, the Connecticut River. All of those rivers, their headwaters are now where the glaciers were, okay? But if you look at, for example, more southern rivers, like the Rio Grande River, for example, or the Colorado River, they did not head onto the Great Glacier Mass themselves, okay? And yet they show evidence of catastrophic flooding. Now, the Snake River that we're going to talk about now, it rose, you would say, near the Grand Teton Dams, Grand Teton Mountains, which, of course, during the Ice Age had a whole lot more glaciers than are there now, obviously. But there was enough water that came down through the Snake River that it completely outsized the flow of the modern Snake River. And it actually, the great flood that came through there is known as the Great Bonneville Flood. It actually started in Utah, Lake Bonneville. So why don't we get right into it here? I have some great imagery here. Yeah, let's do that. I'll go
to draw one comparison to what you're saying, because it touches on what we were talking about earlier. Even something as small in comparison to these cataclysmic events, like some type of solar event happening and overgrazing of the topsoil, and the Great Depression coming on. I mean, look how devastating that was to a society, to our society. Something so small. Imagine an event like this happening. Exactly.
I mean, that's exactly where you're going with your thinking, Becket, is exactly the direction it needs to go. And it's not like, if you're invested in certain prophetic beliefs or whatever, and you believe there's Armageddon is a foregone conclusion. I mean, I know that in some of the great catastrophes, when you look at the human stories of those, like I'll cite, for example, the Great Peshtigo Fire of 1871 that probably killed somewhere around 2,000 people. The greatest natural forest fire disaster in American history, right? Well, you had a lot of the people that were, destroyed in that fire that lived up there along Green Bay, Wisconsin, where this fire occurred, were very religious, and they knew about the whole prophecies and all of that, the idea that of the apocalypse and the judgment day, etc. So a lot of these people, when this whole thing came on, they had time that they could have escaped, but they didn't, because they thought it was futile. They believed that this was Judgment Day and this was the end of the world. And so they just passively gave in, and they were destroyed. Now, had they taken a little initiative and run a half a mile and submerged themselves in the river, they could have survived.
Yeah.
But they thought, this is it. This is the end.
That ideology didn't work for you there. No.
That ideology did not work so well there. And there are lessons to be extracted for sure from these microcosmic scale catastrophes that happen, for sure. So it'd be very valuable to look at some of those.
Yeah, they're nice little warning shots for us.
Yes.
It's even and they're so serious. Like, still, our experience of them, although they might be confined to a smaller geographic area, I mean, you hear about these things and it's sad. Like the fires that are happening in California, I think they're still happening in California. The whole country is there's a different mood about it when it's talked about, and it's so devastating to a society. This would be completely different scales. And I know we're about to look at what that actually, the evidence of that, where there wasn't, and we'll see the people who live there now as we look through Google Earth or whatever maps, we'll see exactly who would have been affected.
Well, let's launch into it then.
Let's do it.
So Harold Mauld, U.S. Geological Survey, 1968, he was the first one who saw, and because of what he saw, he gave eyes to the rest of us. The enormous size of the depositional and erosional features produced by the Bonneville flood imply a peak discharge of extraordinary volume. So nobody before him that I know of really, I'm guessing Native Americans probably had traditions of the flood. I'm sure they did. But they weren't part of the, scientific discourse on, the geomorphological history of North America. So here, 1991, Quaternary stratigraphic. Quaternary is the last 2.5 million years. Stratigraphic, hydrologic, and climatic history of the Great Basin, with emphasis on lakes Lahontan, Bonneville, and Tecopa. And this was published in 1991. Nearly all closed or formerly closed basins in the Great Basin have ancient strand lines marked by lacustrine bars, spits, embankments, terraces, deltas, and wave-cut cliffs at elevations well above the playas or permanent lakes of today. Let's mark. What is a strand line? Well, it's a shoreline. What is lacustrine? That means lake, right? There was a lake there. And all of these associated things like spits, embankments, terraces, deltas that would be associated, wave-cut cliffs. Now, normally a static lake doesn't cut cliffs. You have to have waves, right? And energetic waves. Then you can cut cliffs. And at elevations well above the playas or permanent lakes. Now, a playa lake in the desert is an ephemeral lake. During rainy periods, it'll form, and during dry periods, it'll evaporate away. So it's not always there. So both, as it's saying here, playas or permanent lakes of today. So in other words, these ancient lakes show evidence of being much deeper and higher up than the modern lakes. The impressive shore features of Lake Lahontan and Bonneville prompted their study by the U.S. Geological Survey more than a century ago. About 120 pluvial lakes existed within the Great Basin during Wisconsin time. Okay. Here's the Great Basin. See this? It's almost a circular feature, which suggests to me that it's probably the remnant of some very, very ancient giant impact that occurred early in the Earth's history. And then you've got all of these folded mountain ranges in here. But then what's interesting here is the areas between the lowlands, the range. This is the basin and the range. So it's the mountain range interspersed with these basins, and the floors of the basins are flat for the most part, right? This is the Bonneville Basin here. Have you ever heard of the Bonneville Salt Flats, where high-performance racing cars are tested? Mm-hmm. That's right out here on this big zone right here. This is modern Great Salt Lake, which is a mere puddle remnant left over from late glacial Lake Bonneville. Okay, now what I'm going to do is I'm going to go and I'm going to show you that what you're about to see is not necessarily that all these bodies of water were simultaneous. Maybe they were, maybe they weren't. But the point is this is going to show you everywhere where there have been enormous, deep water over the Great Basin Range, the basin and range. Bonneville was up in here.
So how deep would Bonneville be at that
It
time?
was about 1,000 feet. About 1,000 feet. So, Lake Bonneville became the largest pluvial lake in the Western Hemisphere about 17 to 15,000 years ago. I think it was probably later than that. We can discuss that. But at its maximum, it inundated several coalescent intermontane, in between the mountains, basins in northwest Utah extending into Idaho and Nevada, an area of about 51,700 square kilometers, also almost the area of Lake Michigan, and had a maximum depth of about 315 meters. Today, the only permanent lakes are Great Salt and Utah lakes. Lake Bonneville's history remains controversial. Nearly every serious researcher on Lake Bonneville since Gilbert has come up with a different interpretation. And so, so 315 meters is 1,033 feet. And Great Salt Lake now is, I don't know if it's over 2 or 3 feet deep. It's very, very shallow. 51,700 square kilometers is almost basically 20,000 square miles.
It's massive.
So that's big enough that if you were going to paddle across it, you couldn't see the other side. And when you were in the middle of it, you basically wouldn't see the shorelines. That's how big it was. And you're going to be paddling over a body of water 1,000 feet deep. That's pretty, where it's desert now, basically. So just think about that. Just let that sink in. See? Here's the thing. The dominant dialogue now that's being perpetrated mainly through mainstream media and so on, and academia, is not acknowledging this scale of change that we're talking about here.
It's just small degrees of change that they want to acknowledge, and then anything beyond that gets a little turned head and poo-poo to it.
All right, let's go on. So here's a digital map of northern Bonneville Basin. Here's Great Salt Lake. And then this is the Snake River Plain here. And it's all basalt, young basalts that go back roughly that mostly extruded between about 17 million and 6 million years ago. Still active on its east end up here, because up here is where Yellowstone is. And Yellowstone sits over a magma plume. And the whole southeast base, the whole Snake River Basin here is the pathway of the moving North American plate moving over this hot spot, this upwelling magma plume.
Is that why you get like a lot of hot springs out there?
Absolutely.
Okay.
Yes, that's exactly right. So here's a map of Lake Bonneville. The dashed line here that you see is Great Salt Lake. Can you see that?
Yeah.
Here? Right. So you can see that it at its deepest it passed up into southern Idaho. Okay, so it turned out that, there's one of the things you got to keep in mind here is there's no outlet to the ocean. It's an enclosed basin, right? Until it got 1,000 feet deep. Once it got 1,000 feet deep, what it did was it started spilling over the lowest mountain pass that was on the whole perimeter of and it happened to be up here in the north, right up here. We'll zoom in on that area here. So here's Great Salt Lake, and here is Lake Bonneville, and right here is where the spillway occurred. Right? Can you see where my cursor is?
Yeah.
So that's called Red Rock Pass. So it overtopped this spillway and quickly eroded about 350 feet of relatively soft sedimentary rock. And the lake level dropped about 350 feet very rapidly. Probably over a period of 2 to 6 months it took for the uppermost 350 feet of the lake level to drop. And then underneath that soft sedimentary rock was a very hard granite sill. So the water started pouring over the top of the sedimentary rock, and then quickly ate it down. When it hit the granite sill, it stabilized. Right? Now you had a semi-permanent lake there, but in the aftermath of all the great changes that were occurring on the Earth at that time, this went from a rather temperate zone to an arid zone, and then the water slowly, over a period of millennia that was retained in that basin, evaporated away until all that was left was a puddle, which is now the Great Salt Lake. On the Wasatch Mountains, you can see the high water line and you can see where it dropped, right? And you're going to see that, I believe, in the next few slides. So this is an aerial view shot that I took flying over. This is the Wasatch Mountains. And all of this down here, this transition, represents the shoreline of Lake Bonneville. Right? And of course you see all of this would have been 1,000 feet underwater. Right. Wow. Where Great Salt Lake City is now, that would have been 900 to 1,000 feet underwater. So that shows roughly the lake.
It's massive. It's huge.
So now here, if you look over here on the mountains, you actually can now begin to discern the shorelines. Do you see this kind of horizontal shelf right here?
Yeah.
That's a shoreline.
So where it spilled over, that was where the peak of the mountain was, in the area that it spilled over.
Well, this is a whole mountain range, and it was north of here. This is looking to the east.
Okay.
We're looking to the east at the Wasatch Mountains. All of this was lake bottom. There you see this is a piece of Great Salt Lake down here. Mm-hmm. It's only a few feet deep, right? To the north of here is Red Rock Pass. We'll look at the maps. You'll see how it works. Okay, so now you can begin to see the high water mark traced on the mountain slopes here. Do you see that? Yes. Very distinct. So that's like almost 1,000 feet above the valley floor right there, because these mountains are 2,000 and 3,000 feet up. So let's see, we can go a little further. Okay, check this out. You got this and you got this. So look here. I run the magenta line. That's the Bonneville shoreline, as it's called. And then after the spillover happened and the lake level dropped, it created this second shoreline here. Is it making sense?
Yeah.
Good. Yeah.
How long did the second shoreline stay where it was?
Oh, well, it could have been from centuries to millennia. Again, how fast? I mean, the lake level going from here to here was really fast. I mean, less than a year, probably less than 6 months. There are different estimates based upon, the total volume of the lake that drained. You have to take the area of the lake times its depth. Now, if the peak discharge of the Bonneville flood was 40 million cubic feet per second, how long would it take to drain off that volume of water that could drop the lake level 350 feet? Of course, the thing is 40 million is the peak discharge, right? So you don't know. You need to have reconstruct an accurate flood hydrograph that would show you, because for one thing, as the lake level drops, there's less and less pressure pushing that water forward, right? So the natural shape of a flood hydrograph is a rapidly rising ascending limb if it's a breakout flood, like let's say a dam break flood. It could be, the dam could be a modern dam like the Teton Dam or the St. Francis Dam, that kind of thing, or it could be a glacial dam breaking. But typically you have a rapidly, steeply rising ascending limb, and then it peaks, and then you have a much more gradual, longer tail on that graph that represents the descending discharge rate. And finally, the final stages of it are going to be relatively minor, right? Because It's just leveling out exactly. So you get the picture. So it's not known exactly here because there's not nobody agrees on an exact reconstruction of a flood hydrograph, right? Other than we know from the extent, there are formulas that you can use. Hydraulic engineers use them. One of them is called the Chesi formula. For example, you look at a channel and you look at its channel geometry and you measure the cross-sectional area of the channel. That's the main thing. And then the other thing is the steepness of the gradient. So from there, you can determine roughly what the peak, what the velocity would be. Now, there are other things. You have to introduce usually a coefficient for channel roughness, because the greater the roughness, the greater the turbulence. The greater turbulence, the faster the dissipation of the energy, of the hydraulic energy is going to occur. See, that is going to affect the shape of the curve, of the hydrograph, right? So there's a lot of variables, and we're going to see some of this, as we go through this particular flood. So let's keep going here. Let's see. So right here, follow my cursor. This was the outflow point right up here. By Interstate 15 is actually following the route of the overflow. And what's interesting about that, as I like to point out, is that many of the catastrophically created landscape features we have utilized in building out the infrastructure of our modern civilization. So if you're going to build a highway from these mountains down here out to the Snake River Plain, the Bonneville flood has already created the best conduit for building that highway. Mm-hmm. See? But, well, we see the Snake River right there. That's the Snake. So let's see. Well, I got one here. All right. So, yeah. So here's the passage. Here's the passage through here. This shows the route of the flood. And here was where Red Rock Pass is. So this is where, right in here is where the breach occurred.
And so the breach happened when the level of the lake just kept rising and rising and rising from the flood.
Well, whatever was causing that lake to rapidly fill with water. So that of course raises one of the to my mind biggest question is like, where was the source of that water? The glaciers over the mountains weren't big enough to provide it all, so it had to have been augmented by extreme rainfall. And the rainfall had to go completely way faster than the rate of evaporation. See, the problem is that as the water surface area increases, so does the evaporation, right? So generally, that's what's happening in most of the lakes that we see today, where we're living in a more or less stable environment. So a lake will be generally stable unless there's an anomaly, like an anomalous flood, like what we've seen, some anomalous rainfall that causes the lake level to rise. But generally what will happen is within a few years, it'll go back to its mean level, right? So there's this balance between inflow that can be direct rainfall, or it can be snow melt, or it can be just creek and river runoff that's running into a lake basin. Okay, so you've got the influx, rainfall, overland flow coming in, and then you've got outgo because of as it expands, there's more evaporation, see? So as the lake level gets bigger, it's going to be evaporating and losing water faster. So that is what kind of keeps everything moderate and stable. In the case of Lake Bonneville, it appears that whole process was completely irrelevant.
Because it was rapid. It happened quickly.
Well, that's another question. How rapidly there's evidence that there was a lake there, thousands of years before the end of the Ice Age. However, to say that there's a lake there, there's a lake there now, but it's only a few feet deep. I would say during the Ice Age, because there was additional rainfall and additional runoff, you might have had a lake 200 to 300 feet deep, maybe more. But it does appear that the final span of life of that lake was catastrophic. It rose rapidly, and it had to rise up to over 1,000 feet deep. And then the lowest saddle that allowed overspill for that rising lake was this Red Rock Pass, which is, in this image, it's right here. This is it, Red Rock Pass through here. So the water, and it just so happened that the bedrock there was a softer rock. It was a sedimentary rock that it was not anywhere near like hard granite, right? So once that water started spilling over the top, it was rapidly able to eat it away, and rapidly, and the estimates again that I've seen are anywhere from a couple of months up to a year for that process to take place, where the lake level dropped. But I think it tends towards faster now. I think it's now 2, 3, 4 months, something in that range, that it took for the water level to eat that 350 feet of soft rock away. All the water, so the water level of the lake dropped by that much. And once it hit that granite sill, the flood was over.
Okay, so the spilling over in this case, is that what we're talking about with 40 million cubic feet of water per second?
Yes. That's what we're talking about.
In the previous picture where we were looking at the two shorelines there, is it possible that the lower shoreline could have been where the lake was previously, and then it filled up to the 1,000 shoreline and then spilled over, and then it just balanced back out?
That could be, yes. That could be. It's possible. From what I've seen, I wouldn't think it was that deep for a number of reasons, but kind of technical reasons. But it could have been. It could have been at that level, and then the last 350 feet was rapid. But the thing is that then it would be just a coincidence that the level of the lake before the downcutting of the sill, then it would have just been a coincidence that the water level was the same as the level of the granite sill. But that's what it is now. You can see that the level of the granite sill matches that shoreline. Now, was the shoreline up before the overspill? It could have been, but then, because it's not the density or cohesiveness of the bedrock now that's controlling the lake level. It's the amount of water flowing in. Mm-hmm. You see, so now it could have been, but not necessarily so.
Yeah. So we've got what seems to be like a flood, or at least something making the water level rise very rapidly, which results in another massive flood somewhere. The Bonneville flood.
Right. Well, okay, so the rising, now you're talking about a static body of water, right, that's rising. Now, whether it took several years, decades, months.
We don't know.
We don't know for sure, although I think the evidence suggests it was very quick, like less than a year, that last few hundred feet. Based on other evidence, I would argue that there was a pluvial event. In other words, going back to what we were talking about before with what happened in western North Carolina, what happened in northern Virginia. You had a pluvial event. That means that you had this extraordinary amount of rainfall concentrated into an area. Well, just as we have now seen evidence that you might have flood flows, fluvial events that are hundreds or even thousands of times bigger than what we've experienced in modern times. In the search for explanations, then I think we need to discuss the possibility of pluvial events that are similarly scaled. In other words, how long would it take to fill Lake Bonneville if, for example, you had 20 or 30 inches of rainfall falling per day for a month or two? So every mountain every mountain, stream, and river that's feeding into that basin is now overcharged with huge amounts of water. Rainfall is falling directly on the 50,000 square miles of the basin area. I think that under certain extreme circumstances, it's very plausible that you've got a massively accelerated rate of lake level rise. But whatever that rate was, once it hit that first low shelf of rock, the lowest saddle within the whole perimeter of the lake, obviously that's where it's going to start spilling over. So once it spilled over, and I would also argue and suggest that the peak wasn't right at the beginning. It had to have eaten down, because the more you're eating down, the greater the capacity of the discharge channel to carry larger volumes of water. Mm-hmm. See?
Yeah, and the more velocity there is, and it probably eats it quicker then.
Yes, that's right. So this is in the middle of Red Rock Pass. And the difference here, like the red rocks, which gave their name to the overflow spillway of Lake Bonneville. At this point, the waters of the Bonneville River flowed, actually, it should be 350 feet deep. The rock outcrop here is an eroded remnant of the former landscape. The elevation of the high point on the Red Rock Butte is about 5,050 feet above sea level. The highway is about 4,770 feet above sea level at this point. This is virtually the same elevation as the Provo shoreline of Lake Bonneville. In other words, that lower shoreline that you saw coincided with this level. The upper shoreline coincided with this level up here. So before, this is the rock that got eroded away. So the original spillway was up here. And then the water spilling over, we're looking to the north, the flow is from right to left, rapidly ate down this softer rock until it got to this lower granite bedrock down here. So right here you can kind of see, and you can begin to put all this whole sequence of events back together. And this is the pathway right here. Coming up where Interstate 15 is following exactly the route of the flood. It did a sharp bend to the left, flowed out here, and then it's right here in the area of Pocatello, it spilled out onto the Snake River Plain. And that water spilling out cut a large trough in the basalt bedrock that is now being utilized as a reservoir. They built a dam at the south end, and it's being used as a reservoir to preserve water. But it was originally created by this enormous volume spilling out here.
And why did it take a sharp left? Just the material, the rock it was running into was much denser?
Yeah, well, the slope, this is running up, this is downhill from up here down to here. So it would have been, and it undoubtedly did backflood up for sure. But this is the gradient is from northeast to southwest. So it's basically what it's doing is it's following the slope of the land.
Yeah.
And there's that right angle bend right here, comes out.
So why the right angle bend?
Well, because it's topographical. You can see this area, the water undoubtedly washed. You can see there's kind of a line of demarcation here. Mm-hmm. So as the water rushed here, it would have backwashed up to here, doing two things, washing sediment into the low areas and eroding the high areas down. And you can see that transition right here. This is almost like a high water mark. You see where my cursor is? And then that water would have backflooded up here, but then it flowed out this way.
It's finding, for lack of a better term, like the weak spots where the rock is the weakest.
That's right.
It's just going to erode it.
Yes, that's right. All right. That's where Pocatello is now.
Funny enough, Randall, I didn't realize this, but I hiked in Provo. I went to Provo once, like I guess it was 5 years ago now, and I went for a hike in the mountains. So I was probably right near here.
You probably were. Yeah. So now right here you can see the channels that this water began to cut into the basalt. And what you're seeing here is like what are called recessional cataracts, that when the water picture you've got, let's do it this way, you've got a cliff of rock here, and the water is pouring over it like this. Mm-hmm. Well, as it's pouring over, the erosion, the friction is moving on the rock here, and so what it does is it eats up current. You can see that, right? So it's running over, and it'll pluck rocks, it'll erode rocks, and so the face of the escarpment over which the water is flowing migrates up current. And then at whatever point the waters stop, boom, you've now got an extinct head wall of a cataract there. And that's sort of indication, well, whatever, like you can see many of these recessional, that's why they're called recessional, because they're recessing. And then at whatever point the floods stop, boom, you now have this fossil feature to mark that point right there where. where the
Yeah,
floods
I see.
basically
Yeah,
stop.
so it's you would, I mean, me seeing this without understanding it, I'd think the water would be pushing into it, but it's opposite. It's coming
Yes,
down and
it's coming down.
yeah.
Yes. And these are now looking at some of the erosional. See, so typically, oftentimes in the aftermath of these catastrophic floods, you're looking for very chaotic landscapes.
Mm-hmm.
That's a typical thing that you're going to see is these chaotic landscapes. As it says here again, back to Harold Maude, the Bonneville flood mostly occupied the same canyons and valleys that exist today, but it modified them by causing extensive erosion and by depositing great piles of flood debris. It left a vivid record of its cataclysmic passage. So here are just some statistics on, the area, and this is wrong because this is not big enough. Maximum depth, that's correct. Elevation of the Bonneville shoreline, that's at the high level. Provo shoreline, and elevation of Red Rock Pass. So you can see how close they are to each other.
Right.
Bonneville flood peak discharge was between 35 and 41 million cubic feet per second. The total volume, okay, here we go, was 1,140 cubic miles of water. That was enough to cause the 350-foot drawdown. Assumed duration, several weeks to months. And let's just get to the good stuff here. So this is, we're coming through the pass. This is looking into the pass, looking to the west, and this is showing the direction of water flow. So this was the spillway for the overflowing waters of Lake Bonneville. Flow is from left to right. We call it the Bonneville River.
And that pass was 3 miles wide?
Is that what it says? Yeah, 3 miles wide, yes. And, of course, these numbers have been actually revised upward since I did this. New studies have shown that it was actually a little bigger. So, see, I'm still 35 million cubic feet per second, 300 feet deep.
You're 7 million short on cubic feet per second and 50 feet shallow.
Yeah, so this is overly conservative. But I did this probably 20 years ago. So there have been a lot of new studies since then. And here's an aerial. Here's where that sharp right-angled bend occurs. Water came out this way. Here's Pocatello. So this is where the water discharged out onto the plain, the Snake River Plain. And then as you get down there on the plain, you can begin to, see what's been left, the stuff that was plucked, carried, and dropped. This stuff would have been plucked at the peak of the flood, swept downstream, and then as the waters declined, they would dump their deposits in the landscape.
Mm-hmm.
And Massacre Rocks, this is one of the first of many great boulder deposits you see here, strewn in the path of the mighty Bonneville flood. Note the flood distributary notch here. So this is where it's the opposite of a tributary. Tributary leads into a major channel. A distributary leads out. So this is where the water overtopped the ridge here and then flowed out over the upland and cut this channel here. So that's a distributary. So here, looking at this map, here you can see right here is where that distributary is. And you can also see that that there was overland flow because here are the remnants of recessional cataracts. Remember, water's flowing this way, flowing from upper right to lower left. So you had water overtopping the uplands here, and then it ate in a way, and then it was flowing over and left these cataracts, these horseshoe-shaped alcoves, what are called cataracts, in this case recessional cataracts. So that's a pretty stark indication of the power of this water flow. So, the point here is that once this flood was over and these two rocks they're sitting where they've been sitting for 12, 13, 14,000 years. No force since this flood has been great enough to displace these rocks. They're right where they were put by the waning floodwater. Pretty wild stuff, huh?
Massive rocks, massive boulders.
Yeah. That's Bradley there.
So that's probably 20 feet tall.
Well, yeah, because Brad's, over 6 feet, so, yeah. And this is now the Snake River Canyon, which was definitely over-deepened by the flood. By how much, we're not sure. But you see this shelf up here? Mm-hmm. This might be the former level of the land. Would have been a river flowing here. But 40 million cubic feet per second was a one-time event. And it clearly deepened the canyon considerably. And you have to look for evidence. Where would the previous land surface have been? I think it was probably up in this area up here. And then you have Shoshone Falls, which is this. But it says here it's on the Snake River about 4 miles northeast of the city of Twin Falls, near the midpoint of a chaotically eroded 14-mile section of the Snake River Canyon. Shoshone Falls was an important landmark in the geological exploration of the West, but evidence that the falls are a relic of a Great Pleistocene flood has been recognized only recently. As now understood, Shoshone Falls and its associated erosional features were formed at a time of catastrophic outflow from Lake Bonneville about 15,000 years ago. I think it was actually a bit younger than that for reasons, but so this was published in 87. So like it says here that the falls are a relic of the flood, that's only been recognized recently. See, but here it is. Now, the thing of it is, the modern falls you see here is utterly minuscule. And we can tell you exactly what it is because in a slide coming up, I've got the data on the modern discharge of the Snake River. Shoshone Falls is at the junction of two channels of the Bonneville flood, one along the narrow Snake River Canyon and the other on the upland a few miles north. Where the channels joined, flood erosion produced a chaotically eroded landscape of cataracts, spillway alcoves, and scabland, and the original canyon was greatly enlarged. The main cataracts began 2.5 miles above Shoshone Falls, where the canyon is 230 feet deep. These cataracts, called the Twin Falls, plunge 157 feet from basalt to massive outcrops of silicic volcanic rocks in the lower story of the canyon. The Snake then drops another 212 feet to the threshold of Pillar Falls, 1.5 miles downstream. Now that's a steep drop, 212 feet in 1.5 miles. There's going to be some serious whitewater in there. Pillar Falls, although only 20 feet high, is surrounded by scabland crags that reach 175 feet. So that right there is telling you at least that the depth of the flood right there had to have been at least 175 feet. And this is showing the terrain. So Shoshone Falls is right here. Devil's Canyon is a recessional cataract. So is Box Canyon Alcove. So is Blue Lake Alcove. So what is happening, like right here, you had the main flood channel here, and then you had this overland flow that came here, and they met right here. And then you can see what they're talking about, the chaotic landscapes here. And you see there was a flow coming this way that cut this trough. The turbulence of the flow scoured out a hole that's now occupied by a body of water there. So here's a cataract form. You're always looking for that horseshoe shape for a cataract alcove. There's another one over here. So when you look here at Twin Falls, okay, so here's, at high water, you've got the water basically up to here. Mm-hmm. But this entire terrain up above the upland up here was submerged during the Bonneville flood. So all of this erosion, this was all the consequence of this 40 million cubic feet per second that came through here. The Perrine Bridge, a lot of, bungee jumpers off this bridge.
You ever been bungee jumping?
I have not. That, in the heyday when I would have and could have, it didn't exist. There was no such thing. So this is a great shot. Scale and variance. So here we have the modern Snake River, average annual discharge 56,900 cubic feet per second. That's this down here. And you saw pictures. I mean, it's when you're down standing in the edge of it, it's a substantial river, right? The highest recorded historical peak flow was 195,000 cubic feet per second in 1974. Estimated peak discharge of the Bonneville flood, well, let's say that 40 million cubic feet per second. So you can take your calculator, put 40 million in there.
Okay.
1, 2, 3. And let's say divide by 56,900. And you should have gotten about just over 700 times.
702.98.
Yeah, so now look back at the picture here. You see how the modern Snake is entrenched in the valley floor here?
Mm-hmm.
Well, this is what the modern Snake has carved for itself in whatever 12,000 years. This is the Bonneville River here.
Oh my gosh! Right before you said that, I saw the other
Yes.
peak, or the other, I guess, side of the river there on the right.
Yeah. So 700 times the volume of the modern Snake is what cut this, what I call the Great Bonneville River. So this was that flood that probably lasted, a few months, that all this was cut. So it gets back to questions of what did it? Yeah. And then, now here you can picture, now what happens, Becket, if you've got a narrow passage and the water is flowing through it. Something to keep in mind when you're looking at water flow. Now, the source of the water might be variable, okay? Which means that the flow discharge is going to be variable. If you go down to a major river and it's not in the middle of a severe drought or, a major rainfall event, you can measure the water flow one day and then the next day and the next day, and you'll come up with a sort of a mean discharge, right? Mm-hmm. And what happens then is that when that water is moving, let's say in an easily erodible channel, okay, now you get a flash flood coming through there because of a major rainfall event, it's going to erode, enlarge, and probably widen and deepen the channel. So in the aftermath of the flood, when it's over, there might be actually a new flood. Like I've observed, there's a creek nearby where I live that I've been monitoring for about 30 years now. And there have been a couple of major, when Hurricane Ivan came through, there was such a huge, it was the first time in probably at least 50 years that the water rose up out of the existing channel and spread out onto the floodplain. And it left this calling card of sand on top of the floodplain. Okay, then there was there was an event, there was two events in the 30 years that I hiked down there by this creek. There have been two overtopping events where the water rose up out of the channel, spilled out onto the floodplain. So the earlier one created this layer of sand that's still there, but it's because of the fact that it's been grown over all the years and new soil is forming on top of it. You don't see it from the surface anymore. But if you dig a trench, you would see it. There's this layer of sand. And I can go, okay, that's Hurricane Ivan right there, right? Okay, so then there was the second event, and in the 30 years that I've been, familiar and walking down there by that creek, those are the only two times that the water has risen out of the existing channel and flowed out onto the floodplain, right? So you can look for that. You learn how to look for the evidence, and sometimes it's spectacular and sometimes it's subtle. But you learn how to look for this evidence. It's really like learning a language in a way, because there is a language, or there's an alphabet, if you will, of these features. You've just learned a couple of them. A recessional cataract, right? Mm-hmm. So here you've got a channel, and this is, as it says here, an example of an underfit stream.
Yeah, once you see it, it's very hard to unsee. Because
That's
I
right.
could have looked at this picture before, like, oh, there's a river and a valley, and I wouldn't have. I almost feel silly saying this now, but I wouldn't have thought that that wider thing was a river. Or just
Right.
kind
Yeah,
of looked
no.
at the two sides of it and just been like, oh, okay.
Well,
But now
that's
you see it and you can't unsee it.
yeah, and see, this is the beginning of a sort of an awakening. See, we're on the threshold of an awakening of humanity to this gigantic, epic story that's written into the landscape that we're only now, after 12, 13, 14,000 years, able to actually perceive and then decipher, to actually read the story in the alphabet that it's written in, see? And so now, here's an underfit. You didn't know about underfit stream before, did you?
No, I didn't.
You now know. Here's a perfect example. The modern Snake River we would describe as it's underfit. It's flowing in a channel way outsized that was not created by the modern river that's flowing it. And you can see right here, important principle. Once it's going to be natural that the modern rivers are going to flow in these pre-existing channels. It's also going to be, until you have, think about this modern river is going to be confined to this channel, will never flow outside back up onto the upland unless there was a flood of more than 40 million cubic feet per second that came through here, see? So here's an important takeaway that we can begin to demonstrate now. This one is easily observable because it's out in the middle of a semi-arid plain. But what would happen if you had an underfit river like this, but it was heavily forested? You wouldn't even know that it was you wouldn't know, right? You wouldn't understand. With LiDAR now, we can see through the forests. And guess what we're seeing? Virtually every river in North America is underfit. What does that mean? There are some extremely profound implications to that. That's really going to demand, it's going to require we begin to reevaluate our own history. Because why? It's one thing to talk about an asteroid that kills all the dinosaurs 66 million years ago. It's something else again when you're talking about catastrophic events that our ancestors survived and witnessed a mere 11, 12, 13,000 years ago. See? That's what actually makes this study of this kind of stuff in its own way politically volatile. Why is that? Well, because if people are cognizant of the fact of how dynamic and catastrophic the environmental history of this planet is, well, we might now come back and take a look at the claims for modern climate change and realize that they're just insignificant.
So the reason why this may not have been taken seriously for a while is largely due to money and where dollars are flowing.
That has a big part of it. See, now understand that up until, the 70s and the 80s, it started shifting in the 80s, accelerated somewhat in the 90s, but geologists weren't interested in stuff like this. Mm-hmm. What are geologists? They're looking for hydrocarbons. They're looking for precious metals and ores. They might be mapping the surface, like all the geologists that work for the U.S. Geological Survey that made these incredible topographic maps. They were so engaged in looking at the surface, but they weren't really asking the questions of how did the surface get this way? See, with the rise of uniformitarian dogma, we went from being the biblical age of the earth, 6,000, 7,000 years, to then it becoming several 100,000 years, then to several million years. By the time we got to the point where, who was it? Was it T.C. Chamberlain? Oh, who was it? No, it wasn't Chamberlain. Who was it? It was, he did an estimate. Oh, this was still in the late 1800s, estimating that the earth was 70 million years old. It kept increasing in age, and every time the age of the earth increased and we had more time available, well, here's the thing. The early geologists, some of the very first ones that like Buckland and Cuvier and Roderick Murchison, Sedgwick, Alfred Tyler, all of these guys who founded geology, the modern subject of geology, were catastrophists, right? Now, if you look at the structure of the Earth's topography, and you've only got 7 or so thousand years, means you're trying to compress a hell of a lot of change into a very, very short period of time. Right. The implication is catastrophism, right? Now, of course, in the conflict between science and religion, you know, the entrenched belief in Noah's flood being this supernatural event, and when science finally prevailed over religious dogma, scientists were somewhat averse to admitting the possibility of gigantic floods because it seemed to throw back to biblical literalism, right?
Yeah,
that's where a lot of the resistance came from.
The two.
Yeah. So that was where a lot of the resistance came from in those early days. But interestingly, nonetheless, virtually all the founding fathers of modern geology, from about like 1820 and 30 down up to the closing days of the 1800s, were catastrophists. George Wright was, I think, the last of the 19th century geologists that still was avowedly catastrophist. And I think he was still publishing papers in the literature even into the early 1900s. Anyhow, then catastrophism, when we come into the first few decades of the 20th century, catastrophism was a complete nothing. Nobody was looking at that. Everything was one grain of water, one grain of sand, one drop of water at a time. And if you had tens of millions, hundreds of millions of years, you didn't need catastrophes to create something like you're looking at here. You didn't need a catastrophe to create a recessional cataract or a giant boulder, whatever. So they just weren't looking at it. It wasn't in their framework of thinking. And then when somebody like J. Harlan Bretz comes along in the 1920s and publishes these papers on the Channel Scablands of eastern Washington saying that they're produced by these gigantic floods, the geological community was like, get the hell out of here. Get out of here. We've moved past, giant floods, right? That went out with biblical literalism. So, I mean, he met a lot of resistance from the geological establishment. However, he didn't buckle under. He stuck to his guns for 25 or 30 years, and he amassed so much evidence that finally, basically you had a new generation of geologists coming along who were taking a more open-minded look of his evidence. And his evidence was overwhelmingly convincing that, there's no other way to explain the evidence you've assembled than gigantic floods on a scale unlike anything we've seen in modern times. So it's a very interesting story for sure. Now, I was getting back to this. This water is moving along in a conduit. Now, assuming you're not massively adding to the discharge upstream somewhere, or that it's not rapidly declining like it would if it's at the end of a flood, but it's relatively uniform. What that means then is that, let's say the channel gets narrower and then it gets wider. Well, if you're able to measure the flow rate at a given point, and you can just see this for yourself, if you go down to any creek or river, if you see there's a narrowing of the channel, what does the water do? It speeds up. Mm-hmm. If there's a shallowing of the water, it speeds up. If there's a deepening or a widening, it slows down. Makes sense, doesn't it? Mm-hmm. So the point is, if you've got a smaller channel, you've got more water, you've got faster water moving through there. At the bigger channel, the water's slower, but it's the same discharge volume in both. But because this is smaller, more water has to be moving past a point faster. Okay, if you can get that in your mind, now you know that what happens is, let's say you've got a solid bedrock. Water's going through there very fast, a lot of pressure, a lot of shear pressure against those channel walls. It's plucking boulders, ripping boulders off the side walls as it's going down. If there's a recessional cataract, it's plucking and ripping boulders out of the cliff face. All of that rock is then now being tumbled in the floodwaters. Now let's say that the canyon opens up and you have a basin. The water's going to slow down, and what's it going to do with its sedimentary load? It's going to start dumping, and that's what you see right here. It's exactly what you see right here. So what you see, and you can look at the two human figures out here for scale. It's probably me and Bradley. But yeah, so this is a huge field of where a big sedimentary dump occurred when the water spilled into this wider basin here.
So this is probably the big stuff that it had picked up, because this is right after it slowed down, after coming through a tighter passage.
Correct. That's exactly right. Like, think back to the waterfalls we saw. Well, those waterfalls were created because huge volumes of rock were literally ripped out of the bedrock, and that would have been washed and tumbled down. The farther the rock, another interesting thing is that the farther the rock is transported, the rounder it gets. Plus, it breaks up. So this rock, you can see, is somewhat round. It's not sharp like it's freshly broken. So you know its transport distance was at least probably a few miles, if not 10, 20, 30 miles from wherever it was quarried from the bedrock. If it had gone much further, the rock would have started breaking up, because typically what happens on a gravel bar or a boulder bar is that the larger the stuff will be at the upcurrent end, and then as you get to the downcurrent end, the stuff gets smaller and finer. So so you can see there's quite a bit of rounding to these rocks. But at the same time, you see right here how this rock is not only rounded, but it's broken. So this was a boulder being rolled and tumbled in the current flow, and then at some point it smashed into something and it broke. So you've got a sharp break here that didn't erode off. So it tells you that this was transported some distance in order to get that round, and then at the very final stages of its journey, it smashed into something and broke. And we know that it was the final stages because if it had kept on rolling and tumbling, the sharp edge here would have been completely rounded off. Does that make sense?
Yes.
Yeah, good. Now, when you're looking at this picture, the thing is this is one canyon wall. Over on the other side, on the south side, there's another canyon wall matching this. So I'm down here basically on a terrace that's within the canyon floor. So there you can see a human figure out there for scale. So this thing here is about 3 miles long of these boulders. And the modern snake, of course, has done nothing. This is a fossil feature that's almost as pristine now as the day it was deposited, because no force of nature has affected this landscape nearly enough to really, minor things, here and there, but overall, no. I mean, this is pretty much a fossil feature. Then look at this. So here you have the cliff face, and you see this? I call this wash-up gravel, because as the water is slowing down, it leaves this wash-up stuff piled up against the flanks of the cliffs. If you had a giant broom, you could sweep this stuff away. This is not your normal talus that accumulates at the bottom of a cliff because it's falling off the top of the cliff, because these are vertical shear walls. See, if this was normal gravity-in-place talus, the recession of the upper wall should be equivalent amount of volume of rock as you see piled up here. That's not what this is. What this is the water, the floodwater sloshing through here just wash this stuff up against. And you could dig down and you'd find that there's huge volumes of this stuff underlaying the land surface of the floor of the valley here. Okay, so this whole thing, this is the boulder bar that I was standing on, this whole thing right here.
Wow. How long of a distance is that?
About 3 miles. Well, each square is a mile. You see these squares?
Yep.
So you're probably looking at really like 1, 2, 3, 4. It's probably closer to 5 miles in length. Then what happens when this sediment-charged water, as you can think of it this way, you've got this channel, You got this big flood coming through here, right? Now there are tributary channels coming in from the sides, right? The water is way deeper than the floor of those tributaries because generally those tributaries where the creeks meet the main river, they're pretty much at the same level, right?
Mm-hmm.
Well, if you've got 400 feet of water coming through there, it's going to backwash up the tributary channels, isn't it? Right? It's going to flow up. You're not going to just have a vertical wall of rock there, of water. No, of course, it's going to backflow. Well, as it back surges up the tributaries, it's slowing down. And then it'll reach some distal point at which it'll stop. And when the water in the main trunk valley drops, then the water in the tributary valleys will start draining off. And once the main trunk valley is emptied of flood water, so will be the tributaries. However, remember now you had this back flood moving up, and it's going to be supercharged, not with the boulders, because the boulders are a transport function of the velocity, right? Mm-hmm. This is slowing down, so the water is going to be supercharged with sediment, right? Sandy stuff, silty stuff, fine-grained stuff. As it's moving up, it's slowing down, and it'll finally stop. And then at some passage of time, probably just a matter of a few days, it'll reverse and flow back out. And when it does, what does it do? It leaves a big deposit of stuff. Yep, and that's an example of the stuff right here. You can see. So this is by the roadway, and you can see this is hundreds of feet thick. And this is another way you recognize, because when you have these floods, there are two, they overlap, of course. There's no super fine line of division between the two, but you've got erosion and you've got deposition. Mm-hmm. Clearly, if something is deposited, it had to have been eroded from somewhere else. And clearly, if something is eroded from here and carried into water, it's going to be deposited somewhere downstream. Or, you know, some of it may end up being carried all the way to the ocean. And a lot of this was because this Snake River flowed into the Columbia. And the Columbia was the discharge river for the Great Missoula Flood. Now, to give you an example, pick up your calculator. And we're talking about the Bonneville flood being 40 million cubic feet per second. Mm-hmm. For the Missoula flood, we're talking about peak discharges in the order of 750 million.
Oh, my gosh.
So put in 750 million and divide by 40 million. And what did you get? 750, 1, 2, 3, 4, 5, 6. Divide by 4, 1, 2, 3.
That's almost 20 times as much.
Yeah, something in that range.
18.75.
Yeah, okay. Right. So say 20 times the volume of what you're seeing here. How do you explain that? Well, in my opinion, the standard explanation doesn't make any sense at all. And we won't get into that today. Because there's a lot of evidence that has to be laid out. But as you're going to see here, this event in itself, the more you get into it, the more extraordinary it gets. Now this right here, Snake River, this is at Lewiston, Idaho on the left side here, Clarkston, Washington on the right. So we're basically looking south here.
Yeah.
We're on a big overlook, looking down at the Snake River. This place right here is called Tammany Bar. And there's a huge gravel quarry right here that actually on our last trip out there, we got a specialized tour by the quarry managers. We got in, we were allowed to roam around and explore within this quarry for several hours, which is something I had been wanting to do for at least 20 years. And what we found in there is extraordinary. The guy that took the guide took us through. He knew some of the stuff that was there. He didn't really understand the implications of it, though. I hope that I blew his mind explaining to him what we were looking at. But anyways, this is called Tammany Bar. Now let me show you why this is significant. Yeah, there's the gravel pit. And it's called Tammany Bar because this is it right here. And the Tammany Creek flows out. And there's this big deposit right there. It's right here in the bend of the river, okay? You can see there's this big bend of the river. The water comes around. And always deposits typically occur on the inside of a meander, inside of a bend. Why? Because the water on the inside of the bend slows down, and the water on the outside of the bend speeds up. Because all those little water molecules, they all want to stay together. And so when the water goes around an outside curve, it's just like in horse racing or running track. You know, if you're on the outside lane, you're going to be running farther, aren't you?
Yep.
Well, if you're going to be running at the same distance as all your competitors, you have to be running faster.
Mm-hmm.
The river is flowing faster, and it therefore is on the upside of erosion. And then on the inside of the meander, it's depositional. So right here you have depositional. It's called Tammany Bar because Tammany Creek flows in right here.
Okay.
And there's your gravel pit. Now, what I did, I went there and I went across and found a vantage point on these hills on the other side of the river. Oh, I would have been right up in here looking across at the gravel pit. And this is what it looks like. So here's the channel of Tammany Creek. Here's Tammany Bar right here. Now, right down here, we can see part of where the gravel pit is, and there's actually a cut bank there. It's an exposure of the gravel pit, okay? Well, now we're going to zoom in. So there it is right there. And here's the panorama of what we're seeing right here.
Mm-hmm.
Now look at this. Okay, we got a guy standing here. He's about 6'4" tall, right? There's stuff piled up on the base of it here. But take a look. Do you see that there's two very distinct types of sediment?
Yeah.
Yes. Now, why is that? What's the story with these two distinct types of sediment? Well, let's actually...
So two... Okay, there we go.
Yeah, here we go. Yeah. What's going on here? Now, this is where, to me, it gets so fascinating because really, look, what we're doing here, this is sort of like forensic detective work. Because what we're doing is we're looking at all of these clues that have been left in the landscape, right? And we're trying to reconstruct.
And there's larger rocks on top of this. Like, look at the layers there.
Yes, yes, yes.
It looks like there's like fine stuff, but sitting on top of it is the larger sediment.
Which ordinarily would not make sense.
Which is opposite of what we just talked about.
How do you explain that?
Maybe there's something to do with the sediment on top. That's what it's coming from?
No.
Or
because
two different...
Look, the stuff on top is this is very coarse, darker stuff, gravelly, bouldery. This is like fine-grained, sandy silt. So right here, what you're looking at is two very distinct flow regimes, right? The one down here, the bottom one, the coarser stuff, is obviously a more vigorous flow than this up here, right? Well, all of this is deposits of the Bonneville flow as it's discharging from the mouth of Hell's Canyon. What is this? This is flow coming from Canada. Coming south. Yes. Yes. This is...
Coming south. Okay, so...
It's...
So there's two different floods we're looking at.
There's two... Well, we just talked about the Missoula flood, 750 million.
Yeah.
This is the distal deposits of the Missoula flood right here.
Okay, so what about the rocks sitting right there? That would be the larger sediment from the Missoula flood, like
No,
the
no,
red.
no. The reason is that all of this, the competency of the water that carried this, you have to picture, this is really like almost like thin mud when it reaches this distal reach, right? This is okay, so where you're standing here, the Snake River is right behind me from where I took this picture.
Right.
The flow is from right to left. So the down current is from right to left. So down gradient is from right to left.
Mm-hmm.
This is back floods. It's moving upstream, see? It's moving against the current. It's moving against the gradient of the Snake River right here. Mm-hmm. This is. Well, let's take a look at this. This is the Bonneville stuff. Now, do you see all this layering in here?
Yeah.
Okay, those are called foreset beds. And what happens? Picture this, that you've got, this is not a smooth flow of water. It's water that's pulsing. It's supercharged with sediment, gravel, boulders, all of this stuff being carried in it. It's been moving fast. It's been ripping through Hell's Canyon. It just finished, at this point here, it just finished carving the deepest canyon in North America, right here, right? It's discharged, and now what it's doing, as it moves into this wider area, it's dumping. And all of this foresets, it's moving from right to left, and you can actually see, look, follow my cursor. Here's a pulse of water here. Then another pulse came in, and you can see it overtopped right here. Now, the dipping is a function of how this water is flowing. It's flowing over this mound that it's building there underwater, and it's layering the sediment, right? And the faster the water is moving, the steeper is that bedding. If you're talking about very slow-moving water, the bedding can be almost horizontal. Mm-hmm. But when you speed up the velocity, and all of this supercharged, choked sediment is gushing over, it leaves this layering effect. You can actually see it. It's in laboratory stream tables. They show exactly how it works, right? So anyways, right here you see water moving from right to left, and right up here in the top of the picture, you see the fine-grained silts of the Missoula backfloods. Now, as far as the boulders on top, I think how you have to explain that is that somewhere upstream, probably somewhere in Hell's Canyon, there was a choke point. And it could be, one of the things we know is that a lot of times that landslides on the flanks of river channels occur commensurate with great floods and rainfall. Now, if you had a landslide into the channel, you're going to temporarily dam the flow of the water, aren't you? The water is going to rapidly back up. It's going to create pressure, and at some point, it breaches that temporary clog, gushes out. I think that's how you would explain there was boulders on the top.
And that would be from the Bonneville.
That would be from the Bonneville. Because we can see from the grain size of the Missoula, well, we know where those Missoula floods came from. We can trace them right back up into Canada, and I've done that. I've traced the source of that right on up into the headwaters of the Columbia River, far up into British Columbia. And you can actually follow that route. And what happens when you have this gush coming across eastern Washington, it's moving down gradient as it moves to the south, and then it hits the Snake River. And then when this flow from Missoula hit the Snake River, it reversed the current almost 200 miles, maybe 150 miles, back upstream. So picture this. You've got the Bonneville flood moving downstream vigorously, and then you've got the Missoula backwash coming up that's slowing down. So this is coming down, deposits, then this comes in on top of it, stops, flows back out, and leaves. And we can actually, and I'm going to show you in a minute, we can actually identify where that current reversal took place. And so this is like almost like a cross section. This is almost like an MRI or something, because right here you see you learn to read these effects and put together. Okay, so this is up in Tammany Creek, and this is getting up to the distal region at the point where the Missoula floods finally stopped and reversed current. You can actually see, look here, see this coarse stuff?
Mm-hmm.
That's backwash from the Bonneville. And then on top of it is the fine silts of the Missoula. And when we look in here, we can see something here, the ripple lamination. Look at this. Right here, the water, like I said, remember the bedding? The shallower the bedding, the slower the water.
Right.
So
That's
the water's
slow.
coming in here, it's pooling, it's ponding, and then it reverses current right here. See, you can see it. The current itself has created almost like a snapshot of itself. Right? All of this stuff here, this structure you see here is what's happening in the water. And so the water's slowing down here, and now it's reversing and flowing back out here. Pretty fucking interesting, isn't it?
Mm-hmm. So that's in Tammany Creek. That's what we were looking at, where the bend happens.
Yes, where the bend happens. Right. If I go back a few,
Right there. Yeah.
It's right up in here. So you can see the Bonneville would backwash, but it's going to be coarser. The Missoula flood is going to backwash. But here was the significance of what I saw. And here's what I was wondering. What's on the bottom of the Bonneville flood? That's a question that's been in my mind for 20, 25 years. Since the first time I went out here in 98. I went and went to this site in 98. This was like my second trip back there. This is probably early 2000s when I took this picture. Well, when we got into the quarry last September, there was a deep excavation that was down into sort of a hollow that was in the gravel quarry, and it had exposed what was under this. And what do you think it was? It was this. What does that tell you? It tells me that these events apparently were happening virtually simultaneous. So you had the Missoula flood backwash in, lay down some layered mud in a basin. The Bonneville came washing over that, deposited all of this high energy stuff. Then another backwash of Missoula came in, and so the Bonneville is almost like sandwiched between. Now, the access that I got to see what was under this was, remember, it was kind of in a hollow where this stuff would not get flushed out, because anything not in a hollow would get flushed out when the high-energy Bonneville floods came in. The other thing that's really interesting here, look at the top. Do you see that there's a distinct change between the horizontal laminations and this kind of vertical?
Yes.
Okay, that's 5 foot thick of loess. Now, it's been stabilized by topsoil forming up here, right?
Mm-hmm.
So this stuff is a deposit on top of the uppermost flood layer. What that means is that when the final flood was over, whatever was in the atmosphere began to filter out. And it was enough to make a layer 5 feet thick.
Ooh,
so,
there's some evidence of what might have caused this.
Could be. But, yeah, this is...
So do you think that the two floods, if they're happening simultaneously, could have been caused by the same thing, same event?
Well, see, what you're asking there, Becket, to me, that is the fundamental question that's being raised by this. Because up to this point, mainstream science doesn't see any particular connection between these two floods.
I mean, have they seen this?
There was one paper that I know of that was written on this 10 years after my first visit.
What did they say about it?
Well, I'd have to reread it. But I don't think they got in and saw what I saw. It was Jim O'Connor. He has been studying these mega floods. Really interesting stuff. I need to reread that paper. It was not widely distributed, but most, I've been out in the field with a lot of geologists. I would say maybe not 24, but 15 to 20 up in this area. I've been on field trips. Most of them that I've talked to don't really know about this or haven't done. A few of them, yes, because obviously I learned about this in a paper. But this was, I was scouring the literature on everything I could find on these two floods. Mm-hmm. And then I found this paper that described Tammany Bar, and I said, I got to go see that. And so I did. And these pictures resulted from that. So this is just, this will come into significance later. So,
okay, so we're looking at, just to kind of, I don't know if you're moving on from that or we're closing that out there, but just so I understand, what we're looking at is the Bonneville flood and the Missoula flood. The Bonneville flood is at its peak discharge is 40,000 cubic feet per second.
40 million.
40 million cubic feet.
It's important.
That's very important, yes. And Missoula is 750 million. And Missoula's coming from Canada.
Yep.
And Bonneville's coming from Utah, essentially.
Yes.
And they're meeting at Tammany Creek.
They're meeting right there, yes. Yes. That, which to me, that is... that is an extremely, one of the most interesting outcrops in North America, I would say, because of what it seems to indicate. Let's go a little further with this, and then what I actually want to do is roll this into the whole question of when you raised, so going through all this, to me, of course, the question it keeps reasserting itself over and over and over again is, okay, well, what's the cause? What's the explanation for something like this, right? Now, I'm of the mind that, and this is mainstream geology doesn't go here with this. I believe that we have to look at the outside. We have to look out there, ultimately, to find the explanation. I don't believe that purely terrestrial-based explanations make sense.
If it was to be terrestrial, what do you think it could be? We've talked about volcanic activity.
Well, we can see that up in Iceland right now. We can see that there are volcanically produced outburst floods up in Iceland, and they are locally catastrophic, no doubt. But they're orders of magnitude smaller than what we're looking at here, where you've got literally big volcanoes erupting under the Iceland. I forget the name of it. I think the one of the main volcanoes, I think, is Vatnajökull, something like that. I don't remember the name of the. But yeah, if you pull up a map of, well, hell, I can pull up. I got it open right here. There's a major ice sheet. Vatnajökull National Park. Yeah. I can go share, and I'll do share screen, window. Yeah.
It said 6 hours ago. It said there was a 5.2 magnitude earthquake.
Interesting.
No eruption reported.
Okay, so you've got these large glacier masses on Iceland, and then several of them, there's volcanoes under them, particularly this larger one. And periodically that volcano goes off, it warms up, and it melts and creates a subglacial reservoir. And then that subglacial reservoir will work its way through to the perimeter of the ice sheet, and then it'll burst out in an outburst flood called a Jökulhlaups. And that's where the term for these outburst floods come from. But so my problem is that I've looked for modern analogies, and they're minuscule compared to what we're talking about here. So it's one thing to say that there's, there since the end of the Little Ice Age, there have been quite a few outburst floods documented in Alaska, in the Canadian Rockies, in Tibet, in the Pyrenees, in the Alps, etc. Are they the result of anything exceptional? Well, they're because what happens when the glaciers are melting and receding back is you form ponded water against, like, for example, a tributary glacier may melt and then it's ponded against the main trunk glacier. But at the same time, the trunk glacier is shrinking, the ponded water is increasing, and at some point it breaches a threshold and escapes, usually by finding a fissure through the ice or even going under the ice subglacially. But again, the magnitudes of those are insignificant. Okay, we're going to kind of zoom out now to try to get a better sense of the big picture.
Good plug right there.
So here we have the Pacific Northwest. And we started out this conversation talking about Salt Lake down here. Here's the Snake River Plain, and here's the Columbia Basalt Plateau, and right in here is where the Snake River flows into the Columbia. Well, here's the Snake coming here. It flows into the Columbia here, which is coming out of up here in Canada, right? And then I want you to notice the trending of the valleys here. You see how this is trending more or less north-south? This is trending more or less north-south. You've got all of these long valleys that are trending north-south here, right? Now, all of this was covered in glaciers during the LGM, the late glacial maximum, okay? Important to keep that in mind. Now, look at the Snake River Plain. You see it makes this big arc? Well, around 17 million years ago, this chaotic area right here was over here. This is where, that's Yellowstone Lake right there. The mantle plume sits right under here. This represents the motion of the North American plate over the mantle. Over the mantle plume. So picture this. Here's the mantle plume coming up, and the plate is moving over it like this. So you can actually trace the arc. This is the motion. If you were to play this backwards, 17 million years, this area would go right back here, and it would be here. Now, this area is very interesting. It's very chaotic. Lots of faults, fractures, and in fact, the whole here, all of this is basalt. Huge volumes of liquid basalt that flowed out of feeder dikes that were all in this area right here. For 10 million years, there were these outflows of this outflowing of liquid basalt, forming layer upon layer, in some places several miles thick, right? Layered of these basalts. And then they sort of tapered off and came to an end around 6 million years ago. And they've been mostly inactive, although craters of the moon right down on here was actually extruded about 10 or 12,000 years ago. So it's like there's still some bleeding, if you will. Okay. So what initially triggered this massive outpouring of basalt 17 million years ago? Well, there's several geologists that think possibly there was an impact. And if you had a high dense object coming in at 15 miles per second or whatever, fairly perpendicular to the surface of the earth, boom, it's going to be able to punch its way really deep into the crust. What you're then going to have is what's called pressure relief melting. And it's going to be this upwelling. And I think that's the most likely explanation for this massive basaltic bleed out that occurred that created this whole basalt plateau here. Well, this was the site of these great mega floods that J. Harlan Bretz was studying back in the 1920s, 30s, and 40s. my cursor's pointing to a lake right there. It's called Lake Pend d'Oreille. This is where the water came down this trough right here called the Purcell Trench. Came down here and it spilled out and flowed across the basalt plateau here, hit the Snake, and that's where they back flooded because the Tammany Bar is right in here. So Tammany Bar is right, well, they're not showing. Yeah, okay, so Tammany Bar is right in here. Right here in this area.
Mm-hmm.
The floods came down from this way, and you can see the relationship between the floods and the distribution of glaciers at the time they occurred. Here we go. All right. Here's satellite photographs, and you can see two of the great flood spillways across the basalt plateau. Here's one of them. This is called the Cheney Palouse, and there's another one called the Telford. Now, both of those are coming down. One of the Telford is coming directly off of what looks like discharging from the mouth of where the Columbia River comes out of the mountains and makes this sharp bend to the west right here. Mm-hmm. The Cheney Palouse is discharging from this trough right here. Now, this area between Spokane and Lake Pend d'Oreille is where Victor Baker did his hydrological analysis and realized that the flow coming through this trough right here reached or even exceeded 750 million cubic feet per second. So the bulk of that water came through here and washed down and created what you see here. These darker areas, because what it is you've got several hundred feet of lush topsoil laid like a blanket on top of the hard basalt bedrock underneath it. When the floods came through, they washed away the loess and exposed the bedrock beneath. And that's what you're seeing right here, see? We're not going to get into this now, but at some point we should come back because these landscapes out here are unbelievably spectacular when you know especially when you know what you're looking at. And it's a good way to sort of immerse your own consciousness and awareness of mega floods is to do a tour of these landscapes. So this is kind of the plan for the Bonneville flood we've got coming up. Is we're thinking we would start, in Salt Lake City, and we would follow the route of the flood all the way up to Hell's Canyon.
And when is that scheduled for?
I think we're looking at May.
Oh, wow, that's coming up pretty soon.
Yeah. So this color photograph really...
Yeah, May 11th is what it says on your website.
Okay. So this is taken from 500 miles up. This is one of the early satellite photographs of the Channel Scablands. So here, your Cheney Palouse is coming down here, and this is, you can see down here, it intersected the Snake. So when this water hit here, some of it flowed to the west, which was downhill, and some of it back flooded. There was so much water coming down here that it back flooded up the Snake, and way over here off the screen would be where Tammany Bar is. So are you starting to get how the pieces fit together here?
Yeah, I guess the thing that I don't know, that it's still, I don't know how it would function, how it would happen, is what caused Bonneville Lake to flood so much, the water level to rise so rapidly.
Well, I figure it had to be rainfall. I mean, what else is there? It could have certainly been augmented by snow melt, by glacier melt off the adjacent mountains, because, there were glaciers. But they weren't part of the Great Ice Sheet. Like, this water here is discharging directly from the Great Ice Sheet.
Right.
See? Unlike Bonneville, which didn't. So this is direct meltwater. Bonneville, well, how else are you going to fill up the lake basin? It had to have been rainfall. Now, if they were happening at the same time, which what the evidence at the quarry there, the gravel pit, suggests, is that, do we look for a common cause then? Do we look at something that could simultaneously melt extraordinary volumes of ice and cause extraordinary rainfall, hundreds of miles to the south over Utah? And the answer is, well, yeah, there actually are mechanisms in nature that could probably do that. But they're not of this earth. And that's where this discussion needs to go. Because, see, we've got this legacy from our past. I guarantee, I promise you, Native Americans all over North America have stories and legends and understanding about these events that have been handed down for thousands and thousands of years. Contrary to what the archaeologists are willing to acknowledge, they've apparently done this. They've got stories about these great floods that occurred at the end of the Ice Age, right? So those need to be taken seriously. And when they are, we will realize that the details, even though they sound idiosyncratic and exotic and kind of weird, actually aren't so exotic and can actually give us legitimate insight, valid insight into these events, right? Now, on the other hand, we have science. Like, we're looking at, this photograph here was probably taken in the 1970s, and it was the first satellite photograph of these landscapes, right? So at that point, in the final quadrant of the 20th century is when the human species on Earth begin to realize that there's this whole story that there's no way we can understand the human past on this planet without understanding this story that I'm showing you right here. Because this was a major dividing line. Once you realize the magnitude of this and the scale of it and the scope of it, the global scope of these events, you begin to understand, this was profoundly significant. And we can understand why, what would, in the aftermath of 40 million cubic feet per second, if there had been villages or hamlets or colonies yes, what's going to be left?
Nothing.
That's right. So we won't get into this now. But I wanted to introduce you to this for the simple reason that, we're looking at a bigger picture here. And I don't think that mainstream geologists have gotten a bigger picture yet. Because, see, here's the thing. Just like with archaeology, geology, you tend to look at one particular outcrop. You look at one particular facies, it's called. Or you look at one particular strata and deciphering that. And you might spend 5 years looking at one outcrop. See, there are geologists that are really, really knowledgeable about a particular area, region, the geology of the region. They know the bedrock, they know the petrology, the lithology, they know the groundwater, they know where the ores, they've been, right? But they don't necessarily see how that fits into a larger picture, maybe on a continental or a hemispheric or even a global scale.
Right.
That's what we are going to try to do here, Becket, with this, is we're going to try to bring the big picture. And I think that picture, like I said, I think that once we see the scope of this, we go, okay, if we try to limit our attempts to explain these things by purely terrestrial mechanisms, that's going to be tough. How does that work, right? But as soon as we're willing to transcend the limitations of terrestrial and look at the bigger picture, now we begin to see that, yes, this planet is part of a very much larger ecosystem, and sometimes that larger ecosystem can throw things at this planet that can be profoundly disruptive to the status quo of nature and of human civilization. So that's where I'd really like to carry this conversation, is because, let's put it this way, I think that the cosmos wrote, engraved, inscribed this tale, this epic tale, all over the surface of this planet. And it's only when we've gotten to the state we are now, essentially, where we've got this global vantage point, and we've got these incredible scientific tools that have extended our eyesight into the things that we can see, that we couldn't see a few generations ago, right? So now we're in a position where for the first time in thousands and thousands of years, we human species are in a position to begin to decipher and read this story that is the story of stories, that without which there's no possibility of having any comprehension of the real, authentic, deep story of the human species and of civilization on this planet. Once we've done that, then I think we are by default forced to go, yeah, we have to look at the bigger picture. We have to start looking outside the domain of the earth. And when we do that, yeah, then we're going to discover, well, as it turns out, there are mechanisms that would be perfectly capable, for example, of smashing into an ice sheet, simultaneously fracturing it, melting it, vaporizing it. And that injection of vapor into the atmosphere has to necessarily rain out. It has to rain out somewhere. Somewhere downwind is going to get drenched. And I think we should probably leave it there, because I'm going to get with Chris Cottrell at 8 o'clock, and we're going to do a quick promo that he's going to put out to all the members of All the Randall You Can Handle.
Wonderful.
The Facebook group.
Yep. Awesome.
Yeah.
Well, we'll wrap it up, and that's a good place to end it. Talk to you soon, Randall.